All right. Today we're going to talk about some great theoretical ideas in computer science. In particular, we're going to talk about computability. As introduced by this fellow, maybe the greatest computer scientist in history, Alan Turing. So let's start with the worst possible trope of essay writing. What is a computer? Let's check the dictionary, because actually it will reveal an interesting observation. Okay, so a computer, this is a normal definition with which you're familiar. You know, it's like a machine that you program to do stuff. But if you look, there's another definition of computer, which is a person employed to perform computations and calculations. And the second usage is much older. I mean, the first attested usage in English of computer is from 1613. And like, this is what it meant for, the first 330 years. And then only it meant this for like the last 100 years. Okay, so computers used to be humans. So here are some pictures of computers from the past. As you can see, they're mostly women. Does anybody know where that is? What? Well, yeah. They're like computing stuff by like, there's no physical computers at the time. It's because, they can do the same job as the men, but like it was the olden days, you could blatantly pay them less. So that's the reason. Well, now we don't pay men or women to do this job, so anyway. Okay, so that might lead you to the following question. What is computation, or an algorithm? And something we're going to want to define, and in some sense it'll be inspired by this notion of human computers. So this problem kind of came to be asked around the turn of the 20th century, still before there were actual physical computers. So around this time, this most famous mathematician, Hilbert, gave a famous address to the International Congress of Mathematicians, where he presented what he thought were the 23 most important problems in mathematics, 22 of which have more or less been resolved by now. And his 10th one in his list was quite interesting. This was the 10th problem on his list. He said, given a multivariate polynomial with integer coefficients, just like we talked about in lecture whatever, well, except integer coefficients and there's more than one variable, the task is to figure out a process according to which you can determine in like a finite number of steps whether it has an integer root, whether there's some integers you can plug in for all the variables to get out 0. Okay, if I give you like a big polynomial, it's maybe not obvious how to do that. You can't just like check all the integers. So he's like come up with some kind of way to do this. And okay, around this time, this is somewhat vague, so mathematicians started to think like maybe we should try to actually formalize what an algorithm means. What does that mean? Yeah. Well, no, he just means finite, so yeah. Okay, so this is also the time when study of logic and stuff was flourishing, so people started to think about this. And then 28 years later, he posed another problem which got to the core of things more succinctly. I'll try to read this once. Entscheidungsproblem. problem. It meant decision problem. And here's the problem. Imagine you're given a sentence in first order logic, just like from lecture 3, and you want to know whether it's provable, okay, or whether you can deduce this sentence starting from the axioms of mathematics and applying just all the textbook logic rules. I give you a sentence in first order logic. Can you prove it and deduce it? And he asked to give an effectively calculable procedure, whatever that means, for solving this problem. So, okay, so then people started to think about what does it mean to be effectively calculable, or what's an algorithm, or so forth. So Gödel in 1934 was thinking about this, and he thought of various definitions. This is back before computers, the physical kind, really existed. So they didn't have the notion of computers or programming languages. So this was actually a hard problem to think about back then. So he had some ideas, but he wasn't that confident about them. Then there's this fellow called Church who invented something called lambda calculus, which is kind of, now we sort of recognize it as sort of like a programming language, but, it was some mathematical concept back then. And he claimed that this should be the definition of computability, whatever you can compute using this lambda calculus. But other people like Gödel and this Emil Post, who was also thinking about it, weren't that satisfied because like he invented this like weird lambda calculus and just said this whatever you can compute by this should be the definition of what is computable, but he did not give any like great justification for this. So that was the status in 36. And then in New Jersey, around the same time, there's this very young guy, a British guy, who didn't actually know about all these discussions. But he invented his own idea for the definition of what is computable. So that was Turing. He was 22. And he invented a new model of computation, or it's kind of like a programming language, really, as we'll see, which now people call the Turing Machine. So that's what I want to tell you about in the first part of this lecture. Turing Machine, or TM for short. And he wrote this paper about it in 36, and like basically all these people like Gödel and Klein and Church like read it, and they're like, yeah, he did it. Like it's sort of, you look at his paper and it's somehow just obvious that he did it in the right way, and like this is like the right definition for what something, for the definition of what is an algorithm or what is computable. Okay, so let me tell you about his definition. Also, 1 year later, he wrote a paper showing that his Turing machines were equivalent in power to lambda calculus. So if you believe the Church's hypothesis that lambda calculus should be the definition, then he showed that they're equivalent anyway. Okay, so his inspiration was actually computers, but not the real kind, the kind of today, but like the human kind that only existed back then. And he really imagined, like, what does it mean for like a human mathematician to like compute something? And like he wrote like quite an interesting, like long philosophical discussion of this, which I'll try to boil down for you. He's like, okay, you have a human computer. There's a human. They're like sitting there, like writing stuff with a pencil on a piece of paper. And you can just assume the paper is like a series of squares. And normally it's two-dimensional, but you can make it one-dimensional if you want. And he assumed that the person doing the computation could use as much paper as they wanted. He also assumed that they could only write down finitely many different kinds of symbols, and he had like a long section about how like if you had two letters that looked really similar to each other, then like a human eye couldn't tell the difference between them. So like he's really cared to justify these axioms. And he imagined that a human looks at one square at a time, and they have like a finite number of mental states, and like depending on what they see, they may change their mental state, or like write something on the piece of paper, or like move their pen to the left or the right. And he assumed that humans act deterministically. So he thought these sort of axioms, if you will, of real life captured what it meant for like a human to do a computation. And he subsequently boiled it down into like an actual sort of machine model or a kind of computer language model for capturing this. So I want to kind of describe to you what a Turing machine is by example, and then I'll get to the definition afterwards. So hopefully this will make sense. We'll see. Okay, so now we're getting into a formal definition. So a Turing machine has something called a tape, which is just a piece of paper on which stuff gets written. It's like a one-dimensional array, and it's infinitely long. And it's divided into squares. And to start the computation, like the input is written on the tape, like one character per square. So like the input might look like this. And then the rest of them are blank. All the rest of the squares are blank. Okay. And then there's like the actual machine, or like the set of states. It's called the finite control. It's very much like a finite automaton. I'll explain it more carefully later, but it's like some little automaton that like looks at what's written on the tape and makes small changes to the state of affairs. Okay. There's one more component called the head, the read-write head, and it's like a pointer to a spot on the tape. Okay, and it always starts at the left. Okay, so I'm going to now describe a Turing machine that tries to decide this language. We talked about this language on Tuesday. It's the language of all strings that look like some number of zeros followed by an equal number of ones. Okay, 0 to the n, 1 to the n. Okay, and this is the language that we proved towards the end of Tuesday's lecture that a DFA, a finite automaton, cannot recognize. Okay, it cannot decide whether a given input string is of this form, but a Turing machine can. In fact, I'll try to illustrate how the Turing machine can do this. So how will it work? It gets an input written on the tape, and it's trying to decide if it's some number of zeros followed by some number of ones. So what it's going to basically do is start with the rewrite head here, check that it's a 0, sort of cross it off, move the head all the way to the right until it sees a blank, so it's got to the end. Check that that's a 1, cross it off, move all the way back until it sees a cross off, check that that's a 0, and kind of go back and forth. So I'll try to illustrate this. But what I'm getting at is that there's sort of like a little finite kind of automaton here that controls the Turing machine in a simple way, and it allows it to determine whether or not this string is in this language. Okay. I don't know if I've said this very clearly. Any questions? I'm going to try to illustrate it happening without actually telling you the definitions, and then I'll tell you the definitions. No? Okay, well, all right. So as I said, this is going to be its strategy for checking it. Sort of start at the beginning, check a 0, cross it off, go to the end, check that it's 1, cross it off, and come back. And hopefully it'll exactly match up. So it's going to put like a mark down here and check that it was 0. And now it's going to, as long as it sees a non-blank, it'll keep going to the right. By the way, I'll take this opportunity to give another definition. The tape alphabet is a set of all symbols that can appear on the tape. So in this example, it's going to be 0, 1, this like cross-off symbol, and blank. Okay, so it's going to keep going, and all the while the control is doing a simple thing like, is it blank? No? Then just keep going to the right until it sees a blank. So it's going to keep going, and then it sees a blank, and then it's going to go into a different state that says, okay, you got to the end. Let's go back, check that this is a 1, which it should be if this language is 0 to the n, 1 to the n, and mark it off, and now go back and keep walking until you see a mark off. Okay, so it keeps walking, it sees this, and it says, okay, I know I got back to the beginning. It goes over 1, checks that this is a 0, crosses it off, comes back. Now it knows it sort of got to the end again, so it goes back 1, checks that this is a 1, crosses it off, starts going back until it hits the cross off, comes back. Now it checks that this is a 0. Okay. Now it's going to check that it's a 1, but it's not a 1. Okay, so at this point it says, I reject. This was not a string of the desired form. Okay, so I don't know if that example made sense without seeing the definitions, but if we go back to the beginning, the machine is trying to check whether the input string is of this form, and it does this sort of simple back and forth check. And in this particular case, it's not of this form because there's like a mistake here, so the machine catches it. Okay. Do you have any questions about that, or do you want to wait for the definitions? Maybe we'll revisit this once I see the definitions. Okay. So what is going on in this finite control? It's very much like a finite state machine, a DFA. Okay? It has a bunch of states and transitions that go between the states. Okay? So it has a start state, Q0. And I'll try to explain, this is the finite control that solves this language that we were talking about before, 0 to the n, 1 to the n. So let me just sort of walk you through how it works, imagining the input was this string 0, 0, 0, 0, 1, 0, 1, 1. So this is in the start state. And where you go next depends on what character the head is looking at. So at the beginning, the head is at the beginning, and it's looking at a 0. So it follows this rule. And what is the meaning of this rule? This says if you see a 0, change it to a cross off. And this means go right. That means move the head to the right. Okay? So then it gets into this state. And what's going on in this state? In this state, there's this rule coming out which says that if you see a 0 or 1, don't do anything, just go to the right. And that's what happens for a while. After you mark off that initial 0, as long as you're seeing like a 0 or 1, you just move the head more and more to the right. So it goes around and around and around until it sees, let's say, either a blank or a cross off. And in that case, it knows it's hit the end. So it goes left. Okay? So this is back like when it just finished going all the way to the right. It saw a blank. And it goes 1, and then it moves the head to the left. Okay? Now it's looking at a 1. Okay, so then the next thing that happens is, if it sees a 0, that means the string started with a 0 and ended with a 0. So that's not going to be a string of the form 0 to the n, 1 to the n. So it can immediately reject if it sees a 0. Otherwise, if it sees a 1, it crosses it off. This means, change the symbol that's written on the tape from 1 to a cross off and go left. Okay, and now there's more states. First you sort of check if you're done. If you see another cross off, it meant like the whole string was just 0, 1. And so you can go to the accept state. Otherwise, you have to go to this state, which walks you all the way to the left until you see a cross off, and then you kind of repeat the whole process. Okay, so I don't necessarily expect you to like immediately agree that you read this whole transition and like you agree that it solves the problem. It does, but let me take a question. Yeah. Okay, good question. So let me say what you're allowed to do. The question was, are you allowed to have the head stay where it is? Yeah. The way I defined it, no. So the thing that you're allowed to do is, based on what symbol the head is currently reading, you can change that symbol if you want, or you can write the same symbol back on top. So that's like not changing the symbol. And you always move the head either left or right. However, if you want to have the option of staying put, then you can always sort of accomplish it by having a couple of extra states that like first move the head right, then no matter what you see, don't change it and move the head left again. Okay. Yes? Yes, you're allowed to write the blank. Yes? It may make your code shorter, potentially. Well, I guess it doesn't make too much sense to allow you to stay where you are because, well, you kind of already know what you're reading on the head. So anything that you wanted to do, I see what you're saying. Anything that you wanted to do at that stage, you could just do it instead of waiting. But okay, let me say some more rules, and then I'll ask for questions again. So here's the actual definition. Maybe I should have given this before giving the example, but okay. This is very much like the mathematical definition for DFAs, where it looks like a lot more intense, but it's very similar. So a Turing machine is got 7 components. It's got a set of states. Okay, this is in the diagram. These are like the circles. It's got an input alphabet, which we'll call sigma. That's all the characters that might get used for writing down the input. And we're assuming that the blank is not in there, because you have to tell the difference between just like a blank square and something that's part of the input. And it has a tape alphabet, which is all the stuff that can ever be written on the tape. So that's always includes the input symbols and the blank symbol, and it can have more symbols. For example, in our case, the input alphabet was just 0 and 1. All the inputs were just 0, 1 strings. But we also had this other symbol, this cross-off symbol that we used, which is fine. You can, as long as these sets are finite, that's fine. I'll come back to the transition function in a second. There's a start state, and an accept state, and a reject state. It's a little bit different from DFAs. In DFAs, you can have several accept states. We drew them with the double circles. With Turing machines, it's not a big deal, but you just have one accept state and one reject state. Yeah? It's possible. The question was, if you have an infinite tape, how can you have a finite set of states? Well, we just postulate that you have a finite set of states. But one finite set of states can use an arbitrary amount of tape. For example, you could have a Turing machine that it was in a state where it just always, no matter what symbol it was reading, it wrote 0 to the tape and moved right. And it just stayed in that state forever. So just keep writing 0 on the tape off to infinity. That's a valid Turing machine. It does something weird. It just writes zeros everywhere on the tape, but it's possible. It's allowed. No. So the states do not include the state of the tape. Okay? Here, the states, there are 7. In this example, there are 7 states. There's a finite number of states, 1, 2, 3, 4, 5, 6, 7. in this picture, like these 7 states are up here. So the tape is infinite, but like the rules by which you act on the tape are finite. So it's very much exactly like, imagine you're writing a computer program in Python, and like there was, infinite amount of memory that you could address. Or the input was in an infinite array. So your program itself is only finitely many lines long. That corresponds to like there being finitely many states in the Turing machine. But it could potentially use as much of the memory as it wants. Okay, so let me come back to the transition function. So it's similar to in DFAs, but a little bit more complicated. So the transition function is a mapping, or you can think of it just as an explicit table. It's sort of everything that's indicated by those arrows in the diagram. And it takes 2 inputs, sort of a state and a tape symbol. And it says, if you're in this state and you see this tape symbol, then you change yourself to a different state, and you write a different tape symbol to the tape, and you move the head either left or right. So every one of these arrows in the diagram is like indicating one of these rules. If you're in this state and you're reading this symbol, then you change to this state, you write this symbol on top of the current tape location, and then you move the head left or right. Okay. Any questions about this? Okay, so in some sense, what it's really, it's like a very annoying programming language. But he invented it before. Well, he invented it motivated by human computers to try to capture the intuition that this is all a human can do. So my mathematical definition is capturing that. And actual computers didn't exist back then. So it's like he was writing a programming language for something that didn't exist. Okay, so these are the actual rules of the computation. I think I've more or less described them. The tape starts out with the input string, starts out in the initial state, and the head is in the leftmost square. You follow the transition rules. There's one super little technicality, like what happens if the machine tries to move the head to the left when it's already at the leftmost square. In that case, we'll just say it stays put. And it keeps going through all the states and reading and writing to the tape until it either hits the accept state or the reject state. And if the accept state is reached or the reject state is reached, we say that it halts. And it's also possible, unlike in a DFA, it's also possible for it to go into an infinite loop. For example, this case where it's a very simple Turing machine that just like writes a 0 and goes to the right. It'll just keep going forever, writing infinitely many zeros. Okay, so now, just like in normal programming, you can also write, create things that loop forever. Yeah? Yeah, the question was, can you have a tape that goes in infinite, like both directions, and just have it start at like some arbitrary square? Yeah, that's perfectly possible too. So there are actually some like non-obviously canonical choices made here. Like you could have also had like a 2-way tape instead of a 1-way tape. As I'll try to argue to you soon enough, it wouldn't really change the ability of this thing to perform computation. Anything that you can do with a 2-way tape, you can also do with a 1-way tape. Okay. Any more questions? It's a good time for questions. Yes? I guess so, yeah. You're not allowed to have, at least you're not allowed to have more than finitely many tape symbols. Okay. Let me give you some definitions. Okay, so in the last class when we were talking about DFAs, we had the notion of a language. That's just a set of strings that you might be interested in. Okay, like the set of all strings of the form 0, 1, and 0 to the n, 1 to the n, for example. And we'll say a language, which is like a computational task, is decidable if there is a Turing machine M with 2 properties. First, M should always halt. It should never ever get into an infinite loop, no matter what the input is. Okay, so that's like one sanity condition. And the other condition is that it does the right thing. On inputs that are in the language, it accepts. And on inputs that are not in the language, it rejects. That's what we mean for it to say that like a Turing machine decides a given language. Okay? A Turing machine that has property 1, that it always halts, is called a decider. So not all Turing machines are deciders, but we like the deciders because they always accept or reject. Okay? And so they define a language, the set of all strings that they accept. Okay? And we say that such a machine decides that language. Okay. This slide is just another way to look at the exact same concept. There's an equivalence between languages, which are subsets of all possible strings, and functions, which map every string into either 0 or 1. It's the same concept. If you remember this recitation about the uncountability of the power set of a countable set, you may remember it. Anyway, every function corresponds to a language, and every language corresponds to a function. So if you have a function that maps strings to 0 or 1, the language is just all the strings that it maps to 1. And if you have a language that's like a collection of strings, the function is just f of x is 1 if x is in the language, and 0 if it's not in the language. Okay, so f is like the indicator function of L. So it's the same notion, but we'll sometimes talk about either deciding languages or computing functions. And it's annoyingly, there's a different terminology. So for languages, we say that they're decidable if there's a Turing machine which always halts and only accepts strings that are in the language. Or if we think about it as a function, we call it computable. A Turing machine, computes a function if it accepts whenever the function's value is 1 and rejects whenever the function's value is 0. Okay. So let me give you some examples of decidable languages. So I hope I convinced you that this language, all the strings of the form 0 to the n, 1 to the n, are decidable because I showed you a Turing machine that maybe you can eventually agree does decide it. Okay, in other words, if you think of this as a programming task, like the input is a string and you have to check, is it a bunch of zeros followed by an equal number of ones, then Turing machines can solve this problem. This actually shows that they're more powerful than DFAs, because remember, DFAs could not solve this problem. This is not a regular language. Here's another one that I want to convince you is decidable. It's kind of funny. It's the set of all inputs that are just strings of zeros, and the number of zeros should be a power of 2. Okay, so it's like kind of checking if the number of symbols in your input is a power of 2. It doesn't seem like it's such a hard computational problem. You might ask, can these wimpy-looking Turing machines actually figure this out? But they can. So this is the language. So how do you show it's decidable? Well, you have to show a Turing machine that solves this problem, except if it is a length 2 to the n string of zeros and rejects otherwise. So here's a picture for it. Actually, this uses slightly different notation than the other picture, but I was too lazy to redraw it. So you can, I think, figure out how this works. Well, what the notation means, maybe not how the Turing machine works. But this is how you do it. It has 1, 2, 3. It also has 7 states. Now, you could try to convince yourself that that works. It's not that enlightening, though. So I will take this picture off, and I will describe it in a different way. Okay, and this leads to an important point. There's different ways you can describe a Turing machine sociologically. One way is what I'll call the low-level way. And that means basically giving this picture, literally writing all the states, drawing all the arrows, or writing down all the transitions, and so forth. That's painful, but you may do it sometimes. The next step up is medium level, which is carefully just describing in English how the Turing machine works, okay? And it should be obvious how to translate that into actual finite state-looking Turing machine, but it's making you do a somewhat less painful thing to describe it in English. So once you've done this for a while, you kind of transition into the state where you're well, I prefer to describe my Turing machines a little less formally. And once you get good at doing this, then you might take it to the next level, and you might give what's called a high-level description, where you kind of skip some details and just describe the tricky aspects of the Turing machine. This is for experts only, so you will not get to do this on your homework. But it's better to work at this level because actually describing Turing machines in terms of all their states and everything is a bit painful. So let me try to explain to you why this language is decidable, why there is a Turing machine that accepts just the strings of length 2 to the n. And instead of giving you the states, well, I gave you the state diagram, but it's hard to interpret. So let me give you the medium level description. So this is the English language description of a Turing machine, and I sort of hope you will agree that you can convert it into an actual Turing machine. So let's take a look at it. This first step is kind of the key step. So imagine you've got this tape. It's got some number of zeros on it, and you're trying to tell if that's a power of 2. And the head starts out at the left square. So this is what you're going to do. You're going to have the Turing machine sweep left to right across the tape, and it's going to put a cross out over every other zero that it sees, every other one. Okay, so you can kind of see you'll need like a couple of states to do this, sort of a couple of states to keep track of whether you're, like, gone an odd number of steps or an even number of steps. But this is the sort of thing I hope you imagine you can do. So you go across the tape. Every other zero you see, you cross it off. Now, at the end, okay, as you're going along, you sort of keep track of whether you see a 1, 0 or not, which you can kind of do by having a sort of one track of states to keep track of that. And if you see 1, 0, then you just accept. That's like if the input was of length 1, that's a power of 2, so you can accept. On the other hand, if you see an odd number of zeros, you should reject. It's not going to be a power of 2 if you have an odd length number of zeros. Now let me ask you a question. How can you keep track of whether you've seen an odd number of zeros as you're sweeping across the tape? Yes? Yeah, instead of just having one state where that sort of loops you and sweeps the head to the right, you kind of have two states that you go back and forth between. So you can tell whether you've seen an odd number or not by which one you're in at the end. The most natural thing would be to try to count the number of zeros in the states by like maybe having a state for I saw 1 0, I have a state for 2 zeros, 3 zeros, 4 zeros. But that does not work because you can only have a finite number of states. And you don't know in advance how many zeros you might see. Well, you can keep track of whether or not you saw an odd number of zeros. Okay, so once you get to the end, you see a blank. Then go to another little part of logic that just walks the head back to the leftmost square. Okay, and you have to do something a little bit tricky to like notice where the leftmost square is, but let me leave it at that. And now you just go back to state 1 and repeat this. So there's two things to think about here. Why does this thing correctly decide this language, and why can you actually implement it with a Turing machine with like a finite number of states? So why can you implement it with a Turing machine? Well, you do have to think about it a bit, and you have to think about, for example, how you can keep track of you saw an odd number of zeros or an even number, but I don't want to belabor this point too much. So you can try to convince yourself that it's possible. On the other hand, why does this work? Can somebody tell me? It's actually a loop. It's a programming, it's kind of like code in a weird programming language, and it's got a loop. Yep. Yeah, exactly. So as you're doing this like cross out every other zero, it's basically like in a given stage, you're like taking the number of zeros and dividing it in 2. And you're repeatedly dividing it in 2. If you ever get down to exactly 1, then you must have started with a power of 2. And if you ever get down to an odd number which is not 1, then you couldn't have had a power of 2 to begin with. Okay, so this is how you can solve a pretty easy looking, programming problem in this painful language of Turing machines. So, if you're used to programming, which I guess you guys are, you know that like actually, even with like pretty simple instruction set, if you like do enough tricks and stuff, you can often like do a lot of stuff. And I can't really convince you of this in like 1 minute, but if you play around with it or do some homework exercises, you will begin to see that you can do a lot of tricks and stuff with a Turing machine. So here are some things that you should try in the privacy of your own home. Make a Turing machine that takes an input string and puts a space between a blank between every other character. You basically sweep to the end, move this character over 1, and go back till you see a non-blank, move everything over 1, go back till you see a non-blank, move everything over 1. Takes some effort, but it can be done. Another thing you can do is if you have a Turing machine that uses a big tape alphabet, like 10 symbols, you can get it down to a Turing machine that just uses 2 symbols, or even 1 symbol in a blank. Basically by like having the Turing machine like encode the bigger symbols in binary, you know. This is a one. Maybe this will be on the homework. I'm not sure. But like your Turing machine can take a number written in binary and add 1 to it. You know, you have to have some states for like the carry and the walking back and forth and so forth, but you can do it. This is a good trick if you want to like mark a tape symbol, but like not forget what symbol was on it. You just like add a new tape symbol to your description that's like the old tape symbol with like a mark on top. You know, since you can have any finite amount of tape symbols, that's okay. You can eventually start writing code that like copies sections of the tape around to wherever you want. You can write code to simulate a 2-way tape by a 1-way tape. That's what I just said. You can also write code that simulates having 2 tapes. Okay, and eventually after enough tricks, you basically get to the point where you say to yourself, you know what, I can actually do anything with this thing. You know, at least now we're very used to the fact that like, you know, anything you can do in Python, you can do with Java and vice versa. And you eventually kind of agree that you can also do it with Turing machines. And sort of the most important step, or the most interesting thing that you can do, is make a Turing machine that takes 2 inputs. The first input is the description of another Turing machine, encoded in binary in some fashion. You know, a Turing machine is a finite object, so you can encode it with like some finite binary string. And this machine U takes another string X, and what does U do? It simulates this Turing machine on this string. It just accepts if that machine accepts, rejects if that machine rejects, or runs forever if that machine runs forever on X. Okay, so it's going to have like some part of the tape devoted to like keeping track of M and like what state you're in, and some other part of the tape that's devoted to like the real tape of M on X, and it's going to go back and forth and so forth. But this can be done. If you don't believe this can be done, then you can like look at Turing's original paper, because this is one of the key things in his paper. He showed how to write a Turing machine simulator in like the language of Turing machines. Which maybe, again, is not so surprising. You can imagine writing like a Python simulator in Python, but you know, it was the olden days. It was kind of impressive. Okay, so these are called universal Turing machines. And they're going to be important for us later. So Turing in 1936 invented this definition of a machine and a notion of a computable function or a decidable language. And we may ask, is this a good definition? And as I said, if you play around with this for a while, with our modern intuition, you kind of come to see that, you know, anything that you can compute in like Python or whatever, you could also do with the Turing machine. When I say compute in Python, I mean if it also has access to like an infinite amount of memory. And you're probably also already convinced that like all these machines can sort of, or programming languages can simulate each other. And you know, the only thing I'm really trying to convince you of now, or get you to believe, is that a Turing machine is also equally powerful. It's not less powerful. So this is convenient because, well, you could make a mathematical formalization of any of these languages if you want. But you know, the Turing machine is also a pretty nice, clean one. And Turing machine is also a nice model of computation because you can exactly count the steps. You know, you exactly know what the running time of a Turing machine is. It's literally the number of steps it took until it halted. So there's a very important notion in computer science called the Church-Turing Thesis, which actually says that, you know, these were some examples of ways you could define computation via programming languages. And it says that any reasonable or natural notion of computation you might invent is not more powerful than a Turing machine. A Turing machine can simulate it. Okay, so now this is not a theorem because this is not a well-defined term, natural or reasonable. Okay, so perhaps this is either an observation, or maybe this is a definition of what natural means, or maybe this is a law of nature, or a philosophical statement, or something. Well, it's called a thesis, so we don't know, but anyway, I guess everybody believes it, so this is what we mean. Now, let me ask you a question. Do you think quantum computation breaks this hypothesis? Okay, yes? Okay, well, you said you could simulate anything you do with quantum computation with the Turing machine, but maybe slower. What did you have to say? Yeah, the answer is, yeah, you can simulate quantum computation with the Turing machine. It's maybe slow, but I mean, you guys know from doing homework that you humans can, like, if I give you a description of a quantum circuit, you can figure out what it does, right? So you could also program a Turing machine to do what you're doing in principle, right? And whoa, that's okay. Yes.
Since the quantum states are real numbers and they're
yeah. Okay. Yeah. I know what you're saying. So this is getting at a philosophical or physical point. It's not clear, I guess, really that it's not clear that you can have, even though the mathematical definition of a quantum state is like it's got two complex numbers which are uncountable. It's not clear there's any finitary way in the world of physics to distinguish like arbitrarily close things. I mean, you could even say, forget about quantum and say like, hey, in the real world, I can take a stick whose length is any arbitrary real number, right? So then, like, how could you, somehow this stick has access to like uncountably many lengths, so maybe it could do something that a finite computer could not. But somehow that doesn't seem consistent with physics. Yeah? Yeah, but actually, if you look at a quantum circuit and like you only input like say zeros and ones, and like you yourself can write down the gates, then actually you'll never need arbitrary real numbers. You'll only encounter like numbers that you can write down with finitely many symbols. Okay. Yes, you're worried about simulating randomness. Well, okay, you have to make a definition for what it means for a randomized process to decide a language. So ultimately it has to output yes or no. So usually say if the randomized process says yes with probability bigger than half, we'll count that as it saying yes. And less than half, we'll count that as saying no. And then as long as you can compute the probability, you can say, okay. You can say whether or not this, when viewed as a randomized computing process, would say yes or no. Okay, let me take up more of these questions a little later because I guess we still have lots of slides to get through. But as I said, it's not obvious, and like you can think about it and maybe disagree with it. But we'll take this for now as a thesis. Okay, it's actually good if you believe this thesis because I told you there's 3 different levels at which you could describe a Turing machine, or I could convince you that there's a Turing machine that does something. And now there's a notion of like the super high level, where you just describe any old algorithm you want solving a computational problem. Or you describe it in pseudocode or in Java or in Python. And, assuming the Church-Turing Thesis, anything that you can do in pseudocode or Python or whatever, you can also do with a Turing machine. So that would imply that there is a Turing machine that does your pseudocode. Actually, you could probably prove as a theorem anything you can do in Python, you can also do with a Turing machine. I don't know if anybody's ever actually proved that, but everybody more or less believes it. So generally we assume this, and it's quite believable that anything you can program on your favorite programming language can also be done with a Turing machine. Mm-hmm. Yeah, how do you get a random number? That's getting at the same question that was gotten at before. So you can't with the Turing machine. However, the thing you can do is, say you have a random, your code has a one random coin flip that chooses 0 or 1. you can have your Turing machine just do both of them. Compute what would happen if you flipped a 0 and what would happen if you flipped a 1. And at the end, what your Turing machine will have done is computed the exact probability of every possible outcome. So in that sense, it's sort of like it's done the computation. If it knows for randomized code exactly the probability of every single outcome, then anything you could functionally do with that in real life, the randomized code, you could also do if you knew all the probabilities. Yeah? That's another good point, which is that in real physical life, it's not exactly clear how you get a random number. And in practice, all these programming languages use pseudo-random numbers, which are deterministic, which you could also do with a Turing machine. Nevertheless, philosophically, you might decide you find it natural or reasonable to allow a model of computation with randomness. Then if you do that, then it's still arguable that Turing machines can, since they can compute all the probabilities, you haven't added any real power. Okay, these are all good philosophical discussions. Okay, so let me come to the next question. Is every single language decidable? Or is every function computable? If I give you any old function, is there a computer program that computes it, or a Turing machine that computes it? Okay, the answer to this question is no. And there's a very easy proof of this, that there are some uncomputable languages. Here's the reason. Every Turing machine is encodable by a finite string. So therefore, the set of all Turing machines is countable. It's like the nuclear bomb, right? I mean, you can always describe a Turing machine with a finite string, so there are only countably many Turing machines. And the set of all decider Turing machines is just a subset of all Turing machines. So there are only countably many Turing machines that actually decide a language. So the set of all decidable languages is countable. The set of all computable languages is countable. But the set of all languages is uncountable. This is something you did in the recitation. If you look at a language is just a subset of all strings. And we know that the power set of the set of all strings is uncountable. It's more than the set of finite strings. So there's uncountably many languages, but only finitely many Turing machines or pieces of code. So there's got to be some languages that you cannot compute. Is that okay? Doesn't seem okay, but that's life. Now, you might say, okay, I'm not so sad because, what are these languages that you cannot compute? Like maybe they're just like weirdo languages that you would not want to compute. And here's the real interesting fact, which is proved again by Turing in this first paper, that no, there are some very interesting computational tasks or very reasonable languages that you really would like to write code to decide, but you cannot. They're undecidable. So let me give you some examples of languages or functions, these are the same things, or computational tasks, which you cannot solve by any Turing machine or any computer program. Given two Turing machine, this is a task. I give you two descriptions of Turing machines, or you can think of it as two blocks of code in some programming language. And the task is, do they act the same on all inputs? This is something you might really want to do if you're trying to do program verification, or you're a TA and you're checking like a solution, coding solution somebody handed in. You want to know if this program does the same thing as this program. Can't do it. It's undecidable. It's not computable. Here's a simpler problem. Fix the M2 to be just a program that prints hello world. Okay? So same problem. Given the description of an algorithm, does it print out hello world? Seems like a pretty simple task, right? Here's the code. Does it print out hello world? That's an uncomputable task. You cannot write a second program that will check that. Which maybe at first seems like kind of crazy, but then on the other hand, if you've seen some things in computer science, maybe it's not so crazy. For example, there's this thing, the obfuscated C contest, right, where you try to write in this weird language C that has weird rules, something that does something interesting. So here's a valid C program. Can somebody tell me, does this program print out hello world? No. Well, yes. You can tell me? Okay, I'll come to that exact point in a second. So this is a good answer, but if you just look at it, you're like, I don't know. Turns out it does not. It actually prints out the lyrics of 12 Days of Christmas. But, okay, so actually this question is a good one, though. You know, one thing you could do, probably the easiest thing you could do, instead of trying to decipher what is going on here, is to just run it. Just run it, or write a computer program that simulates it. So what's the problem with that? Why cannot you just simulate it? Yes? Yeah, I don't know. Sure. Yeah, is that what you're going to say?
I was going to say that if you have such a program, you could make another program which takes that program and does the opposite of whatever it says it to.
Maybe. Let me talk about this answer first. So the trouble is you could start running this program, and like you could run it for like 10 minutes, and nothing has happened, but it hasn't terminated yet. So you're like, well, should I run it for 10 more minutes? Or what? Maybe after 10 more minutes, it still hasn't done anything. And you don't know if it's going to like print hello world in like the next minute, or you can't really tell if it's stuck in an infinite loop or not. It's just still going. So you don't know whether you should cut it off or not. That's the real dilemma. Yeah? Time is, for Turing machines, time is defined as, you know, the number of transitions, the number of steps. No. So, I mean, you could simulate, if this were, let's say, a Turing machine instead, you could simulate it for 1 step, 2 steps, 3 steps, and you're like going around the states, and it's like changing the tape and so forth, and like you're not sure if it's in an infinite loop or if it's going to eventually like clear everything off the tape and like write hello world. It's just not obvious. So, for example, here's my favorite programming language is Maple because I do math a lot. So here's a program. Can somebody tell me if this program prints out hello world? I'll give you a minute to think about it. Does anybody know if it does or does not? Yes? It's a very good question. So the question was, is every even number the sum of 2 primes? That's a good question. You see, what this program is doing is checking whether every even number is the sum of 2 prime numbers. And if it ever finds an even number which is not, then it skips out of the loop and prints hello world. Otherwise, it keeps checking. So if you start running this, it'll be like 4, yes, that's 2 plus 2. 6, yeah, that's 3 plus 3. 8, yeah, that's 3 plus 5. 10, yeah, that's 3 plus 7. 12 is 5 plus 7. It'll keep going and going and going. Is it ever going to find one? Okay, well, mathematicians currently do not know the answer to this question. It's a famous problem called Goldbach's conjecture, whether or not every even number is the sum of 2 primes. We don't know. We don't know any counterexamples. So basically, no one in the world knows whether or not this program prints out hello world. And it illustrates the problem. You can like run it for a really long time, and you're just not sure if it's going to stop or not. Yes?
They have somewhere a computer that's just been running this for 10 years.
Yeah, I think this is verified up to like some fairly enormous number.
They have the champagne by the computer.
Do they have the champagne by the computer waiting for it? No, I think everybody actually believes that every even number is, so they expect this to not print out hello world. But that's harder to prove. It could be tomorrow somebody will be just like, check it out, here's a giant even number, but okay. Here's an even simpler problem. This is the most important one, actually. This is a task. I give you the description of a program, a description of a Turing machine, and an input, and I say, if you run this program on this input, will it halt or not? Or will it go into an infinite loop? It's like checking if a program can ever halt. You cannot do that. Even simpler, I give you just a program. It doesn't even have any input. It's just a program. The question is, if you run this thing, will it run forever or will it stop? There's no way to tell. The best you can do is like simulate it for a while, but if it's still running, you're like, I don't know. So this, as I said, is the most important one. It's called the halting problem. Okay, it's a programming task. I give you the description of a Turing machine or some code and an input string, and I say, if you run this code on this string, will it halt or not? Okay, so we're going to prove that this thing is not decidable. It's not computable. And this is Turing's theorem. Turing's theorem is that this halting problem is undecidable. It's not very hard to prove, so let's prove it. It's got a good idea, though. All right, let's prove it. We're going to prove it. So here's the theorem. We'll phrase it as in terms of a language. Let halts, this is a set of strings, halts, be the set of all strings that are the encoding of a Turing machine plus an input, all those things such that the machine halts on this input x. Okay, so you're given a string, you have to decide, is this the encoding of a Turing machine and an input such that the machine halts if you give it x as the input? And Turing is going to tell us that there is no other computer program, no other Turing machine, which can answer this question. Okay, so somebody tell me, what is the first sentence of the proof? Band. Yes. Yes, the first sentence is like, we will use proof by contradiction. Because we have to show that something is not decidable. So let's assume, for the sake of contradiction, that it is decidable. What does that mean? It means we're assuming there is some other Turing machine, which I'll call m sub halts, which is a decider Turing machine that decides this language. So m sub halts is doing something totally amazing. We're going to eventually show it's so amazing that actually we would achieve a contradiction in mathematics if it were to exist. Therefore, it does not exist. And what is this amazing thing it does? It's a program that has the following power. You give it code of some Turing machine m, you give it a string x, and it can tell you whether or not m halts on x. And this guy itself never loops forever. It always gives a yes/no answer. Yes?
So then create a function that checks the answer to that. If it does halt, the function loops forever.
Something like that. There's one additional twist, but it will all fit. It will be an idea like that that will fit on a couple of slides. Okay. We ready, though? So we're assume for the sake of a contradiction that this amazing halting detector Turing machine exists. We're going to get a contradiction. So now I will tell you the description of, hold on to your hats, for one other computer or Turing machine or block of code called D. And this D is going to use this m sub halts as a subroutine. Okay? So D is going to do something also very interesting and amazing. And here's the code for D. Really, I should tell you the Turing machine for D, but I'll just tell you the code. So D only takes one input. The input to D is the description of a Turing machine M. What does D do when it gets M? The first thing it does is it tries to decide the following question. If I were to take M and run M with M itself as the input, what would happen? Now that looks a bit crazy, to take like a Turing machine and run it with its own description as its input. Although it's actually not that crazy, right? Like say you're writing a C compiler and you made your compiler a bit better, then you would want to, say you're doing it in C, then you would compile your compiler with your compiler, right? So you would take your compiler and plug it into your compiler. Okay, so it's not the weirdest thing in the world. Okay, so this is something that D is going to do. It gets as input some block of code or some Turing machine M, and it tries to decide, does M halt when run on itself? And it can do this by using this magic subroutine that we hypothesized existed, m sub halts. Okay? So this will always tell us the correct answer. And as was suggested up here, the last couple of lines of code of D do something also a little bit weird. If this call accepts, then D goes into an infinite loop. It just, it's like while true, run forever. Or on a Turing machine, just keep walking to the right. And if the call rejects, then D halts. It doesn't matter. Let's say D accepts. Okay, so this is, assuming this amazing halting detector machine works, here's a different machine you can do. Take as input M, check if M halts when given its own description, and then do the opposite. Okay. This is the craziest part. We're actually sort of almost done. But any questions about what this means? Okay. So let's analyze this. Let me say in words, to boil it down, program D, if you give it the description of a Turing machine M, it eventually goes into a loop if M running on M halts, and it halts if M running on M loops. Okay, so let's save this sentence up here. So we assume that this amazing halting detector exists for a contradiction, and we use it as a subroutine to make another piece of code that does the following. D on input m loops if m running on itself halts, and halts if m running on itself loops. You may ask why we did this. Well, you'll see in 1 second. So this is now the punchline. What would happen if you ran D on its own description? If you ran this Turing machine using the encoding of itself as the input? Well, we know what D does when you give it any Turing machine as a description. It does this. So that means, by definition, if it loops, then it halts, because this would be D of D. And if it halts, then it loops, because this is also D of D. That's it. Contradiction. Yeah, the end. So it's an amazing theorem. Right? So I mean, this is just mathematically nonsense. You know, you have a machine that loops if it halts, and halts if it loops. That doesn't make sense. Therefore, the only thing that can be wrong about this proof is the initial assumption that this machine, m sub halts, exists. Okay. This is like an amazing punchline in the theory of computation. Any comments or questions? Okay. Great. Turing's theorem. I'm going to skip this, but in some sense, this is also like a diagonalization argument. But I don't necessarily find this more intuitive than what I just said, so you can look at this if you want. Okay, so let me pause on this because it's truly a great idea in theoretical computer science. Just emphasize it, you know, here's the task, you know, given some code, maybe an input, determine if the code terminates or loops forever. Okay? It's not like, oh, we don't know how to solve this problem efficiently. It's not like, oh, we don't know if you can solve this. It's like, we know that you cannot solve this by any program, any algorithm. Okay? So it's a very amazing negative statement. Any questions about the meaning of that statement? Okay, awesome. So we know we know something that you just cannot solve with a computer. Yeah, so if somebody gives you for a homework, like write some code that determines if a given program will halt, you can just hand the homework right back and say, not possible. Okay. You know, getting towards the end of the class, but I regret to inform you, there's one very important, moderately technical idea that you must learn. So even if you're tired, wake up, because this is important. It's the notion of reductions, and we're going to see it several times in the rest of the course. In our proof that this language is undecidable, halts, we use the notion of a reduction. A reduction is really just a fancy word for like using one problem as a subroutine in another problem. So here's the definition. Suppose you have two languages, A, and you should really think of a language as a computational task. Decide if a string is in the language. We say that language A reduces to language B. That means it's possible to decide language A if you had an algorithm for deciding B as a subroutine. If you had it means that you show that if there was a Turing machine deciding B, you could use it as a subroutine to decide A. Okay, it's a pretty simple concept, actually. And this is the notation, A less than or equal to B, with a subscript T for Turing. And you should really think of it as like, A is no harder than B, or B is at least as hard as A. It's like, A is at least is no harder than B. Like, if you could do B, then you could do A. That's what it's saying. Okay? You will inevitably, as you're warming up to this notion, get like the direction of this wrong, but like, it makes sense, right? A reduces to B. That means A is no harder than B. It's like A less than or equal to B. So this is a very important fact. And it's also trivial. I mean, it's immediate. Suppose A reduces to B, and B is decidable, then A is also decidable. It's just almost practically restating the definitions. I mean, A reduces to B. If there's a Turing machine that can decide B, then you can use it as a subroutine to also decide A. Okay? Why is this fact important? Suppose A reduces to B. A is no harder than B. Let's just take the contrapositive of this sentence, which is equivalent to it. The contrapositive of this sentence is, if A is undecidable, then B is undecidable. Okay? Why is this good? It gives you an easy and effective way to show that languages are undecidable. Okay? It took us this like weirdo Turing theorem to prove that halt is undecidable. But now that we have it, we can sort of use it as a black box via reductions to show that many other things are undecidable. Okay, and in fact, if I have time, I'll tell you lots and lots of natural computational tasks that are undecidable. And they all go via reductions. Okay? This is what I said. To show that some interesting language B is undecidable, you can, for example, show that the halting problem reduces to it. So sort of the halting problem is no harder than B. But the halting problem is undecidable, so B must also be undecidable. Because if you could decide B, you could solve the halting problem. So let me give an example. I'm going to define a new language called accept. This is a set of all strings, which are encodings of a Turing machine and an input, such that the machine accepts the input. Okay? So more or less formally, it's like I'll give you the following computational task. I'll give you some machine or some code and input, and I'll say, does the machine accept the input? This is also undecidable. There's no Turing machine that can solve this problem. So how can we show this? We're going to prove that halts reduces to accept. Okay? What that means is if you could have a Turing machine that decided accepts, you could use it as a subroutine to solve halts. But Turing's theorem says that there's no Turing machine solving halts. So that also implies that there's no Turing machine that decides accept. Okay, and now it's actually like a programming task. I give you, like as a black box, like the magical ability to solve this problem, accepts. And you have to write a computer program that, using that magical ability, solves the halting problem. Okay, so let's M sub accepts be a Turing machine, which magical ability to solve this acceptance task. And here's my new program, the description of a Turing machine, which uses this as a subroutine and solves the halting problem. So given its input M and X, I'm trying to decide if M halts when it runs on X. So I'm just going to run M accepts on M and X. And I can do that. I have this magic subroutine. If it says, yes, M accepts X, then I'm happy to also accept. Okay? Because that proves that M halts on X. Not only does it halt, it actually accepts. Okay. What's the next step of the proof? Yeah. Pardon me? Well, that's the thing. What you need to do is now try to decide if M rejects when run on X. The third possibility is that it loops. How can you check if it rejects on X? You only have this magical ability to check acceptance. You see what you can do? So in general, a Turing machine can either accept, reject, or loop. And I'm hypothesizing that you have like the amazing ability to tell if, given a machine and a string X, whether or not it accepts. So if it does accept, then we can definitely deduce that it halts. So we can say yes for the halting question. But we also need to say yes for the halting question if it rejects. So how can we check that, given that the only thing we sort of have access to is a acceptance decider? Yes? Yeah, that's right. So what you can do is, here's the next step in the code, basically. Just what you said. In our overall program that's using M accepts as a subroutine, we take this description of a Turing machine M, and we change it. We change it to switch the accept and reject states. We can do that. I mean, it's not a hard computational task. Just change it. And now call the new Turing machine M prime. It's quite easy to go from M to M, the description of M to the description of M prime. And now we run M accepts with M prime in X. If this thing accepts, it means, I mean, think about it for a second. If this thing accepts, it means that m prime accepts x, which in turn means that m rejects x, right? Because m prime does the opposite of m. So if this accepts, then we know that m rejects x. Okay, so we can also halt and say, or we can also say, yes, m halts on x. Okay, so using this one machine, we can actually tell if m accepts x, and also by reversing the states for the input, whether m rejects x. So if it doesn't do either one of those, then we can finally say, I reject. It means that m must loop on x. Okay, that's a bit of a tricky proof, but we're going to be doing a lot of proofs like this. So it's a good time to ask a question. No? It's okay. Trying to decide if we have time to do another one. Yeah, let's do another one. Well, okay, maybe not. Here's an interesting observation that I want to emphasize. Using the reductions to prove something is undecidable is very funny because the conclusion that you're trying to say is that this language is undecidable. There's no machine that does it. It's a negative result. But how do you do it? You actually do it by constructing an algorithm, the reduction. Okay, so it's kind of a great thing, you know, because we'd all prefer to like program things rather than try to prove like negative mathematical results. And once you have Turing's theorem in your pocket, saying that this one language halts is undecidable, then by reducing it to other languages, you furthermore show that they're undecidable. Okay? So you can actually, in this way, show that many, many problems that you might want to solve are undecidable. Okay, here's one more example, which I'm going to omit for time, but you should study it. Actually, I'll get it started, but I won't finish it. So here's another language called empty. It's the set of all Turing machines that don't accept any strings. So on every string, it either rejects or loops. Okay, so suppose the theorem is that it's undecidable, that there's no machine that can tell, given a second machine, if it accepts no strings. Here's the proof, which again, I'm not going to go over for time, but let me just start at the beginning. The way we're going to do this is actually prove that accepts reduces to empty. Okay? See, now having shown that accepts is undecidable, that was 2 slides ago, now we also have it in our pocket as like a language that cannot be decided. So if we show that accepts reduces to empty, that you can solve accepts using a subroutine for solving empty, then again, we can deduce that empty is undecidable because accepts is. And so given a language like empty, you can try both. Like if you're asked on homework to try to show that it's undecidable, you can try reducing from halting to show that if you're given the magic ability to tell if a Turing machine was in this empty set, that you could solve halting, or you could try to use it to solve accepts, which we also know is undecidable. Okay, and it turns out in this case it's easier to start from accepts to show that if you could have code that solved the emptiness problem, you could also solve the acceptance problem. Okay, so I encourage you to look over this proof. It's not very long, but when you're at home. Okay, so let me end the lecture of 5 minutes with further discussion of undecidability. So these 3 undecidable problems we've seen so far, they all look very much like they're about Turing machines, you know, or code. It's like tell if this code does the same thing as this code, or if this code halts, or if this code doesn't accept any strings, or so forth. So you might say, okay, maybe all these undecidable problems are these like kind of weird ones about checking what a computer program does and whether or not it loops forever. Turns out, however, that actually there are many very interesting problems that have nothing to do with Turing machines that are also undecidable. Just quite interesting. So, you know, the last 10 slides are just examples of such problems. Here's an interesting one. It's probably the easiest one to show that it's undecidable among the examples I'll tell you. It's called post-correspondence problem, or PCP. It was invented by Emil Post. And here it is. These are all computational tasks. So I give you, the input to this problem is a finite collection of dominoes that look like this. And each one has a string written on the top half and a string written on the bottom half. Maybe there's 3 of them. And here's your, we'll say a match is a sequence of these dominoes where repetitions are allowed such that the top string is the same as the bottom string. Okay? So you can have as many copies of these as you want. You're just trying to put them in a row such that the string formed on the top is the string, same as the string formed on the bottom. Okay, so here's an example of a match. You do red, blue, black, blue. You see the top is A, B, C, C, A, B, C, C, and so is the bottom. Okay? Doesn't look like the weirdest problem in the world. You're given these dominoes, and the question is it possible to make a match with them? You might imagine that, I don't know, in some course, it might be a homework problem. Try to write a program that solves this question. I'll give you the dominoes. Can you make a match? Yes or no? Well, it's undecidable. There's no program that can solve this problem. Okay? Which is kind of amazing. It doesn't look like there's any Turing machines or anything weird in it, but you cannot solve this problem. So this language, more formally, if you make it a language, PCP, the set of all domino sets such that there's a match, it's undecidable. And okay, this is not really a proof sketch, but in 2 seconds, how do you prove this? You reduce from the halting problem, just like before. You show that if you could solve this domino problem, you could use it to solve the halting problem. And it's like some tricky construction where like you make a domino set that has something to do with the states of the Turing machine, such that the only way you can make a match is by somehow like constructing an execution trace of the Turing machine that accepts. So that's it. So that shows that you cannot solve this domino problem at all. Okay. This one is very similar. It's called Wong tiles. I give you a finite collection of tiles that are squares, and they have colors on the corners. And the test is, can you put these together so that you always have color matching and cover the infinite plane? Okay? It's undecidable. Okay, here's another one, modular systems. I'll give you a bunch of rules like this. If you have ax plus b, you can derive cx plus d, where a, b, c, d are integers. And you also have as input u, and the question is, can you get to v? Okay, here's an example. I'll give you 2 rules. If you're at 2x, you can go to x. And if you're at 2x plus 1, you can go to 6x plus 4. And you're trying to get to 1. Well, if you've ever heard of this famous in mathematics 3n plus 1 problem, it's equivalent to deciding if you can get to 1 from any number u. And this problem is also undecidable. Let me skip this one for time. It's also interesting. This one is also interesting. This is called the mortal matrices problem. The input to this problem is 2 21 by 21 matrices of integers. You get 2 21 by 21 matrices. And the question is it possible to multiply them together, like do A times B, then B times B times A times B times B times A, to get the 0 matrix? This one's also undecidable. So all these tasks cannot be solved by any algorithm. And let me end by going to the Hilbert's 10th problem, which sort of started the lecture. This was you're given a polynomial with integer coefficients, and you're trying to tell is there an integer root. Okay, that was shown undecidable by these 4 people. And it's kind of amazing because Hilbert's, his original question in 1900 was like, give an algorithm for this problem. And there's no way he would have guessed like the correct solution would be there is no algorithm. I mean, he really thought there was an algorithm, but it's solved. There's no algorithm. Whether it has a real root, that's actually decidable, which is kind of amazing. That was by Tarski. Whether it has a rational root, it's not known if it's decidable or not. Okay, well, we're out of time. This problem, if I give you a sentence and ask whether or not it's provable, that's undecidable. And we'll see that when we do Gödel's incompleteness theorem.